This demonstration illustrates a tool utilized to analyze vulnerabilities exploited by CGC POVs. This command names a CGC session in terms of the challenge binary, the round, the attacker, and the defender. The tool references the CGC game archive to retrieve RCBs, filters, POVs, and seeds to reconstruct the named session. The resulting files are pushed into the forensics harness that is emulating 3 servers: the POV thrower, the IDS, and the defended host. Then the named session is run. When the session on the emulator encounters something interesting, the local IDA Pro is automatically started and its debugger attaches to the Syncs GDB server, which has been activated on the forensics harness to facilitate interaction between the IDA debugger and the forensic harness. Here in the bookmarks window, we see that this session resulted in a Type 1 POV. These bookmarks are automatically generated by the tool to indicate locations of interest. These 2 bookmarks, indicated as ROP, are places in the program where the program returned to locations that are not calls. This second ROP isn't a true ROP, it's simply a return to an invalid address that results in the segmentation fault. This first ROP entry tells us that we transferred execution to this address 804.8309, which happens to be this POP. So this is how we entered into this code segment. I'm going to ask the tool to jump to this bookmark, which is the first case of ROP that we recorded. And we see that we're executing out of the heap. Turns out that this challenge binary allocates this memory area with the execute bit enabled, which is poor programming but very convenient for this POV, allowing it to put its payload here, which happens to be a simple stack pivot redefining the stack around the content of EAX. The fact that there are no other ROP entries in our automated analysis suggests that we got here through a function call. I'm going to test that theory by asking the tool to reverse to the previous call on the call chain. Here we see that the IDA debug menu has been augmented to include reverse execution functions, and I will ask it to reverse until the call. It does that, and sure enough we see that the call is a corrupt function pointer that took us to the payload. This begs the question, where did the content of ECX come from? So I'm going to ask the tool to reverse trace the data to find the source of that register. The tool works backwards, and we see that the data originally came from a decree receive call. If I look at the registers, I see that the receive call brought data into this buffer, which happens to be a 1-page statically allocated buffer within the program, and I read in 1 page worth of data. If I look at the bookmarks, I see the reverse data trace, which is backwards in time, and if I start with the kernel receive function, I see the movement of the data through registers in memory all the way back into ECX. If I jump to one of those execution points, I see that the overwrite likely occurred within a memcopy operation. If I then reverse to the invocation of memcopy, and look at the call stack, I see that memcopy was invoked with the source being the receive buffer and the data being moved into an address that looks suspicious. It appears to be part of the process's initialized data. So at this point I'd like to know where this address came from. Why is the program moving data into this address. To do that, I'm going to do a reverse data trace on the content of the memory that holds that address. And when I do that, it takes me back into the malloc function. And here I see that this address is being adjusted, apparently to account for a heap chunk header. And if I continue backwards, I see that the address originally came from initialized data as part of the implementation of malloc. That seems like a bug in the malloc implementation. And if I reverse to the invocation of malloc, I see that malloc was called to allocate a very large buffer, and that is indeed the intent of the CB author, was to have this result in an integer overflow, causing allocation of a too small buffer, allowing the POV to overwrite data structures within the heap. None of the POVs exploited that vulnerability. Rather, they took advantage of the problem with the implementation of malloc in order to simply overwrite the function pointer.